this morning is Babis Anastasiou, on Higgs Hadroproduction, a laboratory for predictive QC.
Good morning. Thank you, Hendrik, and the present organizers for the kind invitation to be here. I feel a little bit exotic. I'm not talking about amplitudes, I will talk about amplitude squared, or cross-sections. But I'm also allowed to use optical theory, so I can fall back into the community in this way. So, I will talk about Higgs production at Hadron Colliders, and more specifically, I will focus on the work that I'm doing with my collaborators on gluon fusion, and how we try to push the precision of this cross-section to next to in order imperturbative QCD. This is work done in collaboration with Claude Bull, Falco Dulat, Elisabetta Furlan, Thomas Gelman, Franz Herzog, Achilles Nasopoulos, and Bernhard Nisberger. And in the last part of my talk, I will try to go a little bit further than what we have done in published work, and I will tell you a bit about explorations that we are making into making the calculations less inclusive and more differential, and this is with a new generation of students together with older generations, Simone Leonetti, Bernhard Nisberger, Andrea Pelloni, and Caterina Specchia. In the last few years, there have been two important breakthroughs in phenomenology. One is in the news, and it's very much celebrated, rightfully so. And it is, in fact, that we have the Large Hadron Collider, a machine which produces outstanding results. They discovered the Higgs, but what is also very important is that they have an amazing precision across a big spectrum of observations. However, this is not the only breakthrough. I think in our community we understand very well that experiments need theory, and they need one part of the theory which is not just the Lagrangian, but we need to take the Lagrangian and transform it into predictions, into numbers and cross-sections. And luckily, there has been a huge breakthrough, which has its, let's say, big moments, but also it has some continuous progress that takes place all the time in perturbative QCD. These two things together, breakthroughs in simulation, in perturbative QCD, and breakthroughs in measurements, they give us a very certain way to go about finding new phenomena and new laws. It's not the only way, but it is an established way, through precision, to try to figure out whether we understand high energy physics as we believe we do or not. So, we have a theory, a standard model theory. We have to sit down and compute the consequences of this theory, and then we have to compare it to LHC. And when this does not really work out very well, we have to repeat the cycle. We have to get inspired again as theorists, formulate new candidates, theories for replacing the standard model, simulate again, and so on and so forth. Obviously, we can be successful in finding new laws of physics through precision as far as we have precision. So if we can simulate to a level of 10%, then we can discover beyond standard model phenomena that they should show up bigger than this 10% in the observations. So how well we do in simulation, in computing from the Lagrangian, the cross-sections, is of paramount importance for the precision program of the LHC. Higgs production has been one of the driving motivations for simulating more precisely at the Large Hadron Collider. So, Higgs is produced in very many ways. Some of these ways, they come with other particles together with the Higgs. So for example, if you look at associated Higgs production with the top pair, and you produce a Higgs through other tops, the tops decay into W's and bottoms, the W's decay into fermions. You get very complicated final states. Or with boson fusion, through the fusion of W's, producing a Higgs, you also have associated jets with that. And of course the Higgs decays on its own, so the final state can become as complicated as it gets for at the LHC. It is important to say that not all of these processes have been studied yet to the finest precision. So, for example, TT bar Higgs, we just see first evidence and associated Higgs production with boson fusion. It is, of course, detected. On the other hand, it would benefit a lot for further precision studies. What does this mean for QCD? It means that we have to be able to simulate for the signals, but also for the backgrounds, multi-leg processes, many legs in final state. But there are also simpler ways to produce the Higgs boson. For example, you first produce a W, it emits a Higgs and a W. This is still a 2-to-2 process in practice before you allow the Higgs to decay and the W to decay. It becomes a multi-leg final state when the decays take place, but okay, we can separate the problem in a reasonable way and to a great accuracy in this way. And still, what happens here is, since we have an effectively 2-to-1 process, we can focus on getting more precision by accounting for virtual corrections, for loop corrections, not just going to more legs, but also more loops. And this is also great because in the gluon fusion process, which is mediated through a top torque mainly, but not only that, we can have very high precision from the experimental measurements. Now, we are used to think of gluon fusion as a process where two gluons go through a top quark loop and they give you a Higgs. But when we tackle the cross-section to a high precision, and there are also other ways that you can produce the Higgs from gluons. It can be a bottom quark in there, which is now important for actually understanding the cross-section that we get from the data, and also ways that you have the gluons making a quark loop, and these quarks connect to W's or Z bosons, which eventually they give you Higgs boson. So not only QCD is important, but electroweak corrections are also very important. I say that, I will say it also later on, because we are a community that has contributed enormously to perturbative QCD. However, I feel that we understand how to do perturbation theory in general quantum theory. So I think that sometimes it is important to also not forget electroweak corrections, because maybe right now, if we want to improve on precision, maybe the shifts should also go to electroweak corrections as well, not just QCD corrections. Now, Higgs production is one of the examples which challenges us for higher loops and higher multiplicities of our processes. And here is a very rough summary. I apologize if it's not exactly how many of you think about it. It's not supposed to be very accurate, especially this big statement that I say, that if you look at one loop processes next to living order, then the problem is solved for many final state particles. But so what do I mean by solved? One could argue that NLO had already been solved on its genesis when the whole thing started 2-3 decades ago. Because technically we know how to do one master universe since many decades, and in principle we have a method, Asarino method for example, which tells us how to do these calculations on paper, or maybe on a computer. However, these techniques, although they solve the problem in theory, in practice they don't do it. So when I say a problem is solved, I always want to connect this solved relatively to the precision that we require and the multiplicities that we require to simulate in experiments, not like reality. So the claim is now that at NLO we have very many processes that they cover more than the most important parts of LHC phenomenology. Of course, you can challenge me here with salt and say, well, let me give you 50 final state, 50 particles in the final state. You cannot do it. And this is clear. Perturbation theory can never be solved in any way, at any order, in physics. Even at field level, we can stop being able to simulate because of computational power. But, okay, this goes beyond what the LHC wants to measure. And now, for smaller multiplicities, 2 to 1 and 2 to 2 processes, we can go beyond NLO. These are smaller effects than NLO. NLO gives you a precision of about 30%, let's say. If you want to calculate better, you can go to an NLO, and this gives you a precision of about 10%. In the last few years, this has been an enormous progress as well. So first, we have many methods right now, but they solve the infrared problem. They tell you how to combine numbers together, cancelling the infrared divergences and getting numbers out once you know the loops. Also, we have a huge progress in calculating loop articles that you, of course, know very well and have driven as well this progress. And there are situations that this 10% may not capture, may not be comparable to the precision of the measurements. For example, in Higgs production. So you may want to even go to something like a 5% precision. So it is motivated to go to next to leading order, next to leading order, and to below for some processes, like in the group fusion. Now, here I say that many of the problems are unsolved, while here I say that many of the problems are solved at NLO and at NLO. And you may get the impression that going from one order to the other, perturbation theory changes a lot. This is true when you go from NLO to NLO. Techniques you can apply at NLO, they profit a lot from the specialities or the special simplifications you can find at NLO. When you go to NLO, there are things that are different. For example, the reduction methods, they start relying more on integration by parts. The master integrals, they need to be computed more especially, they are more challenging, and so on and so forth. So, if you know how to do NLO computations, it's not clear that you can do NLO computations. But when you go from NLO to N to below, I think that the nature of the problems does not change significantly. There is a gap in difficulty, but it is more of the type of the gap that one encounters when you go from Passarino-Bernoulli reduction with unitarity techniques, right? So you have an in-principle solution, but if you can get in practice the result using these techniques, is not clear. So here, I would say, we do need more powerful techniques, but it's not like that the techniques that we have at NLO cannot get you to do an NLO calculation. So I will discuss a little bit later about the techniques in more detail. So after this general introduction, let me say what I plan to discuss specifically here. I will give you a bit more motivation about the gluon fusion cross-section, why we need computed law and Cuban law. I will mention the techniques that we are using for that. And the calculation is not finished. It is finished for many practical purposes, phenomenological purposes, but theoretically there are still some open things to do. I will give you a status of the computation. I will discuss the results with the danger of boring many of you, discussing uncertainties and scale variations and things like that. But I thought that I need to motivate why we do things and what we can do next. And in order to do that, we have to see what is the impact of our calculations in practice, in the precision of what we are computing. So I will discuss phenomenologically the results, and then at the last part, I will talk about some first ideas that we have on how to go to differential prosections. So why do we want to be more precise in gluon fusion? Well, the question of how many Higgs bosons are produced at LHC is an important one, because it will be related to what the experimentalist measure directly. And concretely, if we know how many Higgs bosons are produced at LHC, then we can improve how well we measure the couplings of the Higgs bosons, of the Higgs boson and the standard model particles. This is also necessitated because the measurements are going to be very precise, but a precise calculation is going to be used at the end. So here is a plot made by CMS where they predict how well they are going to measure the couplings to the tau, to the top, to the bottom core, and effective coupling to gluons, to the Z boson, to the W, and in fact effective coupling to photons in CMS after they get an enormous amount of data. So this will be 2035 more or less, but this will be accumulated in 2020. And the big bars here show what would be the precision if we don't do anything to the gluon fusion cross-section. The red is if the gluon fusion cross-section is calculated with zero precision. Of course, we cannot calculate with zero uncertainty. Sorry, we cannot calculate with zero uncertainty, but the result, if we have, for example, the uncertainty, would be closer here rather than here. So any progress we do in gluon fusion cross-section calculations will have an impact in the extraction of the Higgs couplings. So this is a big motivation. The other motivation is that the uncertainty that it is assumed with the computation at next to leading order, in particular 2CV, is a bit shaky. So this is the cross-section at leading order as a function of the normalization and factorization scale. And you see you get a very monotonic, useless result because you cannot find any stable point. The scale is a fraction of the Higgs boson mass, so it typically a physical scale should be around the Higgs mass or a little bit less than that, half the Higgs mass. So you expect your answer to be lying more or less here physically. When you go to NLO, you get a big correction as well, and also a very bad monotonic behavior. Here, you still hope that your result will be here, okay? But the fact that you got a huge jump from here to there makes you to feel a little bit uncertain that this could be a good estimation, because in practice you could also jump up to here if perturbation theory is not really convergent. So if the next leading order result is bigger than the leading order, the next leading order correction is bigger than the leading order result, this is really not a sign of good convergence. And when you go to NLO, which happened something like 13, 14 years ago, you get for the first time a change on the monotony, and you get an intersection where the physical scales lie with the previous order. So you start getting more confident that the cross-section is somewhere here, and based on that, if you believe that, the scale variation is about 10%, and you can claim that this is the ultimate precision at this perturbative order. Still though, it's not clear, or it has not been clear entirely to the community, that the cross-section has converged. So, there have been studies before an exact N-Kubelot calculation based on soft factorization, which tells you how much they expect the cross-section to be once the next to the order corrections are computed. And this is as a ratio to the N and N. These are different groups, people using the same soft physics to calculate, to make a prediction. So for example, I'm here, I was unable to make a prediction. More expert colleagues, they work with soft exponentiation for a long time. They were trusting their results better, so they have less uncertainty. But they found big corrections with respect to N and L. If the jump from here to here is real, then it's as big as going from NLO to NLO. So again, it puts into it puts into trouble the convergence of perturbation theory. So both because of phenomenology, because the 10% is something that the experimentalists are going to surpass easily, and because of not being entirely sure that the NLO result is accurate enough, one has to go to N-Kubelot. But this is a difficult problem because jumps in perturbation theory do not come easily. So we have to understand what happens at one order either. It has been important during this project to figure out a good division of the problem so that we can attack it. One natural division of the problem is diagrammatic. If you use the optical theorem, you see contributions with a single cut over the Higgs, or a cut over the Higgs and another parton, but then also two loops on the other side here, three cuts on partons and the cut on the Higgs, which has only three-level diagrams and so on. So there is you need to calculate counterterms as well, and so on and so forth. So there are many distinct pieces to attack, and the techniques that one uses from one to the other, they are a little bit different sometimes. Nevertheless, this division alone of the problem does not make it more manageable. We need to do also another simplification. So the simplification to go from NLO to N-Kubelot that we used was not to calculate the cross-section exactly, but to first calculate it in the limit and then as an expansion around this limit. This limit is when the center of mass energy is equal or close to the Higgs mass. So the Higgs boson is produced at threshold. So Z is very close to 1. And the cross-section has some expansion in 1 minus Z, which probably reflects how much energy is left to gluons that they can be radiated in association with the Higgs boson. So the job was to not compute the full series, but let's start computing some of these coefficients here. And here is the progress that has been achieved. already before we started the calculation of NQ already in 2005, from the fact that the infrared divergence is cancelled, and from the fact that we knew splitting functions out of this monumental work of Vogt and Vermasseren, we could predict the logarithmic pieces of the first term in this expansion. In 2014, we could compute the full first term, then the next. Then there has been a change in our technology and in the approach. If we continue this way, without changing the techniques, we would be very, very, very slow. And here, we changed method, and we were able to compute something like 37 terms in the expansion. And what now needs to be done, not only for aesthetical purposes, but also for practical purposes, is to calculate the cross-section in a closed functional form. Why do I say this? An expansion around threshold with 37 terms gives an adequate result for the LHC, where the truncation uncertainty of this expansion is at the level of about 0.5%, conservatively. We try to be conservative. If you want to apply the same calculation to another process, like Drell-Yan production, Drell-Yan already at NNLO is known with a precision of 1%. So if you are going to NQ, probably this uncertainty should tend to be a few per million. If your truncation uncertainty, because you cannot do the full result in a closed functional form, and you do an expansion, is 0.5%, then you don't really have a prediction to the accuracy to claim NQ. So understanding not only the expansion, but the understanding all of these elliptic integrals that they start to emerge at NQ is one of the important things that they have to happen in the future. So here is a list of all the pieces that they have been attacked with many authors. Many things happen from the Zurich group. It's not really a Zurich group because we are dispersed, but luckily all of the people that they work on this project within our group had a stay in Zurich for some time, but now they are populating the world. But there have been many works from other people as well. And although we are the first to arrive to the final result, I'm pretty confident that this calculation will be repeated by more than one groups in the future. So let's see diagrammatically what has been computed. The three loop, it's known exactly, it's just numbers. The real virtual is also known exactly. Real virtual squared, known exactly. Halo terms, known exactly. Not published yet, but Claude and Bernhard and Falco, I think they have finished exactly the calculation of the real virtual. And the only piece that we know we needed to resolve an expansion at the end was the triple real, where it's only 3 diagrams, but the integrations over the phase space are very, very complicated. The fact that we know so many pieces exactly gives us the opportunity to calculate coefficients of logarithms exactly as well. So this is another decomposition of the cross-section. There is a term which puts the Higgs boson exactly at threshold, and this we know exactly, it's numbers. But there are terms that they come with a logarithm of 1 minus z. And for a from 1 to 5, when we really have a logarithm, these functions, by demanding cancellation of different divergences, are computed exactly, and the only piece that we need to know as an expansion is the constant term, is the non-logarithmic term. So, let me now discuss how has it been possible to compute this cross-section at the below, exactly or with the expansion. And the techniques are many, but I'm not, so I don't have time to describe in detail. So I'll just restrain myself to explain why now. What was not known before and is known now, and how did we exploit that? So, looking at the names of the techniques that we used, you will say, oh, everything existed before. So we have not really done much of new things here. However, one has to say that in recent years, there has been an explosion of techniques that came up for loop calculations. And this recent progress was very important for us as well. So let me give you some examples of old ideas and how we use them in this new setup. One idea that one has to use is unitarity, or in the specific case of our calculation, what we call reverse unitarity. So we found easier to do phase space integrals by just mapping them to loop integrals, taking delta functions with Katkovsky rules to propagators. This has already been used at NNLO for calculating the gluon fusion cross-section. What we use right now is that once you are in this representation, then the Katkovsky rules on the right-hand side can also be differentiated with respect to parameters, mathematical parameters, like the mass of the Higgs boson. So you can make an expansion around threshold at the level of the loop integrals that they originate from phase space integrals. Another very well established technique is the Laporta algorithm for reducing to master integrals. This is a simple thing conceptually. It's just Gauss elimination if you want, but one has to say that it is responsible for 99% of the progress that we have done since the invention of this algorithm. And nothing changes in the algorithm from NNLO to below, but you just find out that the programs that we and other people have programmed before to do this Gauss elimination are not good enough for NQLO. So you really have to implement, again, being more sophisticated and gaining any efficiency optimization you can. So this was really nothing new, but without redoing it, we would not have arrived at the result. There are many other tricks that one used. So dimensional shifts, Mellin-Barnes, multi-dimensional integrations, poly logarithms, and so on and so forth. All of these names existed, but there have been important changes that they helped us in the last few years. For example, when now we have a multi-dimensional integral, we can figure out an order in order to attack, an order of integration in the integration variables. So in the past, when you had 5 dimensions to integrate over, you would try the first one and the second, maybe it's not good, you go to another choice, and so on and so forth. The order of integration would be random, and you would have to try many of them until you figure out what was the correct one. But now there are theorems that they came out of this community, and that they say how we should attack this multi-dimensional integration so that it can always stay, if it is possible, to a basis of polylogarithms. We have to represent phase space integrals in a clever way. We have to use Mellin-Barnes as well. What is usually done is that you start from a phase space parameterization or a final parameter parameterization, and then you go to Mellin-Barnes. This was in the past. What we also found useful is to take the Mellin-Barnes representations and go back to some final parameterization type of integrals with less dimensions. So this is not, so we use Mellin-Barnes as an intermediate states rather than a final state. Then the enormous progress that has come up is the techniques of symbol and coproduct and the differentials that they are used for for iterative integrations and understanding polynomials. I think without this, things would have been extremely difficult. When we managed to shift from being able to do an expansion of 2 terms and to get an expansion of 37 terms, we changed the techniques. And the technique that we use was the technique of differential equations. The technique of differential equations can be used, as you very well know, to solve the problem exactly, if you can. And recently there has been an enormous progress by figuring out how to find the correct basis for your master integrals by Johannes Hehn. But you can also use this method to solve differential equations as an expansion, and then you have to combine it together with the method the strategy prisms to calculate boundary conditions. So this was an old technique, but we had to give it a new tweak as well in order to make the computation. Now, when we did this transition, many things changed. So we had to have many more Feynman integrals. At NNLO, we had 27 integrals at the level of masters, but we arrived at a level of 1,000 master integrals at the NNLO. And the boundary conditions for solving differential equations, they were not a handful, but they were something like 72 or so. So this was a very complicated problem, and it had a complicated engineering side as well, how to keep track of all of these various contributions correctly and combine them together. So let me now go to the results. So here is what happens when you have the n below prediction. Again, the rule here is the leading order. This is the next leading order. Here comes the N and the O, and here is the scale variation at n. And you see for values of the normalization scale, which is close to what you expect to be physical, the behavior is quite stable and quite, actually, it's more or less flat. So the scale variation anymore at the below is minute, and on top, it's very nice that the tubular result is not higher, but it is very close to the end of the law. So the predictions that one should have a big jump from end of the law to tubular law were wrong. So now we have confidence that the perturbation theory, for all phenomenological purposes, has converged in this process. Let me now go to the results. What I showed there was purely perturbative QCD, but in order to get a phenomenological answer, you need to do more than that. You need to combine with other things. For example, L2 So our calculation was done by integrating out the top quark and assuming that there is going to have a coupling to the bottom quarks or light quarks. This is what you can do at the below. If you don't integrate out the top quark, you can just do it alone. And if you have the light quarks, you can also do it alone, maximum. You can get some terms as an expansion in one over the top at n and n as well. And you also have to include the Lefebvre corrections. So here is the budget of how much every term contributes to the final answer. So this is the leading order, integrating out the top quark. Here comes the next leading order. You see that this is bigger than the leading order, so this makes you worry. Here comes the end and the low. It's 10 picobarns instead of the 20 that the end and low was. And here comes the end to the low. It's 1.5 picobarns, which is small and is actually what you want to see. If you correct to and low for the fact that the top quark and the bottom quark have a finite mass, then you also get a negative correction here, which is a 4%. And the electron corrections are also big. There are 5%, which goes in the opposite direction. So combining all of these things together gives you an uncertainty which at the total is about plus minus 5%. So here is the decomposition of the uncertainty. We have an uncertainty because, which is at the 4 per mil level, because we cannot calculate everything exactly and we have truncated. We have a scale variation uncertainty, which is very small in comparison to what it used to be at n below. We have an uncertainty because we don't know the partial distribution functions in the same order as n below. We know it only through n below. Electron corrections, and the fact that we have top bottom quark in the field. So because of the finite mass of the quarks, we have a +1 and another +1, 2% uncertainty together. So why do I show this table in this audience here? I do this because I believe that many of you can help to make further progress and reduce the uncertainty more than that. So for example, if we manage to do exactly at NNLO the cross-section calculation without integrating out the top quark and taking into account the bottom and chunk quarks, then these 2% will go away. And if we manage to do the next order in the electron corrections, this 1% will go away. So this is a 3% altogether, with another 3% here. So by just doing two very well-defined calculations, one electron weak and one NNLO, but with masses inside the cross-section, inside the Feynman diagrams, then we can halve the theoretical uncertainty in Higgs production. And this is extremely important for the LHC. I think this would be amazing. Just have the theoretical uncertainty with a 3%. Now, what would it take to do electron weak corrections, for example, at the next order? Already the electron weak corrections are known at the next order, but in the limit that we assume that the W and the Z mass are higher than the Higgs mass, which is unphysical. So one limit is known. And in that limit, the 3-loop diagrams for the electron weak corrections, they collapse into 2-loop diagrams, and one can do them easily. So if we want to do this type of electron weak corrections at the 2 below, we will need 3-loop form factor diagrams with masses inside. So therefore, we are going to have to tackle the problem of elliptical influence. The same holds for the 3-loop diagrams that they are needed for an exact NNLO computation of light core contribution. So, for our community, the progress that we can make in elliptic universe and understanding massive propagators inside our loops will be very, very important, and I hope that in the next 5 years these problems are solved and we have a much better understanding. Even other things are going to become better by a more general progress in our field. We don't know the PDF functions at N2 below because Higgs is the only process that we have computed at this order. And also at the previous order, at NNLO, we don't know the jet cross-sections exactly. So if you wish, our PDFs right now, they are not even NNLO. They are just NNLO plus many NNLO processes. So by computing more processes like jet production of NNLO, and perhaps one more process which is sensitive to the gluon fusion, let me dream, top pair production of NQLO, for example, or Z plus jet at NQLO. or photon flare so that is too below. Then perhaps one can do better removing this as well. This will be removed by computing the cross-section in a closed functional form. So at the end, we will be left with a plus 0.2% minus 2% uncertainty for the cross-section calculation. So I think it's very important to work through this table. So let me show you the final result when we combine all of these uncertainties. It's plus 5%, minus 6%, minus 7% almost here on the theory side. There are other uncertainties from alpha strong and PDF here as well. And if you compare it to what one expected at the end of the law, this is exactly half the uncertainty that we have achieved by one of the higher ratio. I'm not sure how much time we have. So now let me talk about another challenge that we can face at this order, at the below. We computed the inclusive cross-section, and this is a very useful result terminologically, because the experiments can extrapolate to measure their measurements to calculate the inclusive cross-section. But it would be better if instead of doing an inclusive cross-section, we were differential. And to be able to account for the acceptances of the experimentalists directly in our results. Now, traditionally, this has happened already at the end of the law. We first did the inclusive and then we went differential. And the question is, can we repeat this at the end of the law? There are quite a few problems, so let me show you a few of the problems that I find that one can find. In principle, when you say you want to be differential, and you have already done the inclusive, it looks like you have done already the work, in the sense that the inclusive cross-section is an integral over differential cross-sections. So somebody would say, just don't do the integral, and then you have the differential cross-section. And this is correct in theory, but there are complications that have to be addressed. So when you are differential, instead of a one-scale problem, just a Higgs mass, you have a many-scale problem. You have angles and energies of all particles that are involved in the final state, and you have to keep track of them. And the biggest problem that one faces is that what it used to be inclusively a dummy integration variable, which you could treat in all possible ways without regard to its nature, now is a variable that it has to be respected, in the sense that it is a variable which will be measured experimentally. So when you have an angle, you cannot just integrate it out. Because if you integrate it out, you lost information about the angle, and the experimenters are going to measure the angle. So let me give you an example. Let's assume that x and y are two physical variables, like energies or angles in this integral. And here is some complicated, in the sense of overlapping singularities, denominator, which emerges from final diagrams. So notice that when x and y together go to 1, then you have a singularity. Okay? And it is regulated, here I just put an A, but in reality it's regulated by the measure regularization. This J function here is a function that the experimentalists are going to write for you. It is 1 when the experimentalists measure, and it is 0 when the experimentalists don't measure in this corner of the phase space. So we don't have control over this, and for every infinite safe definition of this J function, our job is to produce a result for this integral. Okay? So we don't just need a number here, we just need to know these integrals as a function of j, where j is not given to you. So this is a problem. Now, we can do that very simply. We can do sector decomposition or nonlinear mappings and factorize the overlapping singularities and then subtract the singular pieces which will correspond to j to x equals 1 and y equals 1 in here and get a numerical answer. This is how you would do it differentially. But these techniques of subtracting the singularities when they come in an overlapping fashion, they have been understood now at n level, but they are not really understood at n level. So it's a challenge to do that. Now let's look at the same integral and see why this could have been much easier when we did an inclusive calculation. It was easier because we were allowed to integrate out the physical variables. There was no j function here given by the experimentalist, the j was 1, so we could integrate everything out. And in the process of doing that, we could exchange physical variables with Mellin-Barth variables, which are entirely unphysical, like complex variables. These two integrals are the same, but there is no mapping from these x and y variables to these w1 and w2 variables. The volumes are the same of the integrals, but there is no transformation which takes the integrand from one to the other. And when we use such a trick, where we say the volume of two integrals is the same, but I don't care to map the variables from one to the other, then we lose information that the experimentalists are going to need to have. Now, if you think about it, most of the techniques that we have used at NQ below do exactly that. They integrate out physical variables. Reverse unitarity, when we map phase space integrals into loop integrals and do integration by parts, integrates out variables. Final parameters, for example, it's a definition of integrating out momenta and exchange them with final parameter integrals. Differential equations, the integrals we get there, they have nothing to do in terms of a one-to-one transformation with the original integrals that we have over phase space or Mellin-Barth. So if you want to do differential computation exactly, then you have to give up on all of these techniques that you integrate out physical variables. And you realize that this is actually very, very tough. Now, there is another big challenge that we have. As I told you, at the two below, we needed to do an expansion calculation. And the technique is complicated because it combines strategy of regions, it combines reverse unitarity, it integrates out physical variables. So also this expansion seems not to be available to us if we want to go differential arithmetic. So practically what I'm saying to you is that doing the inclusive calculation seems to have been much easier than one thinks on doing the fully differential calculation. I wanted to also point out a problem about the expansion around about the expansion and being differential. So let's take an integral which has no divergence, but there is a small parameter like the energy of the gluons, and you have two variables that if x and y goes to 0, physical, then this does not explode because this small parameter protects it, but this will give you logs and so on. If you want to expand around this small parameter, inclusively you can do many parts, you can do strategy of regions, for example. So what does it mean? If you can see this integral here scales from 0 to infinity, you can scale x with respect to delta and y with respect to delta. And immediately you get all the behavior as delta goes to 0 as a prefactor. So there is only one region with a mathematical strategy of regions for doing such a type of integral. Now let's suppose that you become differential and you don't integrate over the x variable. So now you cannot just scale y with respect to delta, and you have also to think about the hierarchy, whether delta is smaller or bigger than x as well. So suddenly you get more regions. Okay, let me discuss now how we think we can not solve this problem, but at least arrive to some place where we can exploit many of the simplifications we see in the inclusive prosection, but still to be able to do some differential stuff. So the idea that we have is that we don't want to solve all of these problems, but at least let's only be differential on the Higgs momentum. So when we do the phase space integration, the experimentalists are going to introduce a function here which knows about the components of the Higgs, but the X-ray radiation, they don't touch it. They don't measure jets, for example. They don't put a jet meter and so on. So if we do that, we can factorize a phase space into a phase space for the Higgs times a phase space for the X-ray radiation. And the idea is to be differential in the Higgs and inclusive in the radiation. So what happens then? Well, we have tried it at NNLO, and we have found that surprisingly the calculation is not very, very hard at NNLO. So at NNLO, we have found that we have, for double radiation, we have essentially 8 master integrals. The double line is the Higgs where you cut, but practically think of this line to be open since you cut on every component of the Higgs momentum as well. And on top, we realize that all of these master integrals, they are just one upper hypergeometric function, which originates from a single type of angular integration. So instead of going to momentum space, but doing integration by parts and other things in angles, then we see that the problem is much, much simpler at the end. And I must say, I find it much simpler to do Higgs differential NNLO than to do Higgs inclusive at NNLO. So the hope is that maybe we can do things a little better also at NQLO. And if we do this halfway, Higgs differential radiation inclusive at NQLO, maybe we have some chance. Very preliminary result, this is a rapidity distribution at NNLO. This result is known in the literature, but we have done it now point by point here instead of bins, histograms. And we also have the terms at order epsilon, which are going to be used for renormalization at NQLO. Okay, let me add my conclusions. I just told you how we went through this NQLO computation for Higgs production. I hope I convinced you that the results are important for phenomenology, and I hope I convince you that there are open problems like electroweak corrections or finite bulk masses or differential production of Higgs at NQLO, which are more tackling in the future, and they are going to have an impact on the phenomenology. So I just feel that this is the beginning of NQLO phenomenology. I don't know how far one can go, but it's definitely worth to try. Thank you.
Thank you. Any questions for Babis?
Hi. So you said that you're very close to getting the exact results at NQLO, right? What is the remaining challenge? Is it hard to write the differential equation in normal form, where epsilon decouples?
Let me be clear. When I said we, I don't mean myself.
I'm sorry.
In the sense that I think this job is done by more experts than me in complicated functions like Claude and
Okay.
happen better.
Well, maybe I can ask a different question.
But no, I mean, I can tell you, I understand that there are some functions that they seem to be elliptic at the end. And I believe that they can be done. I mean, you don't need, in order to get the answer about them, you don't need to know everything about elliptic functions. I think that the problem can be isolated to expanding a couple of integrals around one limit and the other limit and reconstructing the whole thing, or you can do it in very few integrals.
So you're saying that this is a good example where the soft limit really helps you, where you really have a much simpler class of functions.
Yes, when you expand around the soft limit, or when you expand around the higher density limit as well, which is also a possibility that we have not used. This is extremely good, and then you don't see any of these problems.
Can I also ask you why you say it's not possible to use reverse unitarity at the differential level? I mean, as far as I understand, there should just be some theta function constraints on your phase space, but I mean, I've never tried it, but it seems plausible at least that because the derivative of the theta function is a delta function, I can just rewrite my IDP code and do everything exactly the same way.
I don't exclude that this is a possibility to do it this way. I just don't, I mean, this is one of the thoughts that we also had at the very beginning when we were doing reverse unitarity, but I practically found it very cumbersome because you have to introduce for every theta function, which again is not given to be in a nice form, de facto, by the experimental selection. You have to introduce at least one more integration, and then to do reverse unitarity, and then undo the integration, or do the integral. So I'm not sure it's straightforward. It doesn't look straightforward to me.
For sure, it's not straightforward.
Yeah.
In principle.
But you know, you are younger than me, so you have to try it. So.
I mean, for the more restricted goal of getting the doubly differential cross-section, though, you would think something like what Rob's suggesting could work. In fact, we worked on the rapidity distribution, used reverse unitarity, right, with the L functions. And then for the PT distribution, that's subject to things like QT subtraction. Would you combine the two?
So actually,
and there are NNLO codes now doing Higgs plus jet, which is the sort of the piece of the non-PT equals 0 bin.
yeah. So I'm not claiming that this is the best thing you can do at NNLO, right? What I'm
saying at NQ.
At NQ I don't know. So this is not just the rapidity distribution. I show only the rapidity distribution because only one of us has made the numerics and we have not checked anything else. So I thought I shouldn't show many results that may not be correct at the end. It's double differential liquidity and rapidity. And the experience has been that if you just do rapidity, life is complicated. If you are double differential, life is very simple. And I think what is the correct level of differentiality, if you will? You have to be as differential as you are permitted to factorize the overlapping singularities. If you are differential in the next variable and you don't introduce overlapping singularities, then you have to do it. When you start introducing overlapping singularities, then you have to go inclusive. Now, the idea is that once we have this double differential, then we can think about slicing methods, for example, that they can make it fully differential. And also, we have found that for the radiation inclusive part, besides the fact that we have extra variables, we can do a threshold expansion as well, and we can do reverse unitarity. The radiation inclusive part is done with inclusive techniques. But the outside part is done numerically. I don't know if I answered your question.
Final question for Babis?